Okay, we're going to go ahead and solve this optimization problem where we're finding the dimensions of a rectangle whose perimeter is 100 meters and whose area is as large as possible. Okay, now on an exam or maybe in a homework assignment or something similar, I'm not necessarily going to tell you that the problem is an optimization problem. Okay, so for this example, I sort of have that in the title, but that's not necessarily going to be the case when you see these types of problems. So we need to sort of use the clues in the problem to tell us what we're trying to do with this problem. Okay, now the clues for an optimization problem are usually language that tells you that something is the best it could be. So this might be language like largest. That would be the best, the biggest something could be, or maybe smallest. Okay, maybe you want to minimize something. You see the words maximize or minimize. Anytime you see words like these that tell you something is the best at whatever it's trying to do, okay, whether that's the smallest or the largest, you're gonna look for optimization techniques. Now, when you see these types of words, that means we're trying to find global max or min on a certain interval. Okay, and typically these problems also give you more information. So here we're told the perimeter is 100 meters. Keep those things in mind because that information is going to be necessary later. Okay. The first thing we want to do is to sketch a picture. So here's my rectangle. And I know something about its perimeter, and I want to determine something about its area. So I should give names to the sides of my rectangle so that I can write down equations for these quantities. Now, a rectangle has sides where the opposite sides are the same length. So I'm going to call the two sides here x and x. The other two sides might be of different length than these vertical sides. So I'm going to give these a different name. I'll call them y and y, but they will have the same length as each other, right? The opposite sides will be the same length. Okay, the area of a rectangle, which I'll call A, is length times width. So here I'll say that's x times y. And this is the object that I want to maximize. So I'll just make a note of that here. This is what we want to maximize. And if you think back to when we talked about the extreme value theorem, that told us how to find absolute maxima and minima on some interval. In particular, it told us to check the endpoints of our interval and the critical points. Really, the extreme value theorem tells us that if you have a function that's continuous on a certain interval, then the absolute maximum or the absolute minimum occur at the endpoints or critical points. Well, that means we need to find the critical points of this expression. The only problem right now is that this equation has two independent variables. Okay, so notice that there are two independent variables here. And we, at this point in our mathematical careers, only know how to take derivatives of functions that have one independent variable. For example, f of x equals x squared. We know how to take that kind of derivative. We don't know what to do when there's two different variables. That's where the extra information is going to come into these problems. We're going to use this extra information to get rid of one of these variables so that everything is just in terms of one variable. And then we can take derivatives and do all the things we know how to do in calculus. So let's see what this tells us. The perimeter is 100 meters. The perimeter of a rectangle is the sum of all the sides. So x plus y And I know that the perimeter of this rectangle is 100 meters, so 100. So really, I know that 2x plus 2y equals 100. Okay. I didn't even really need to give this a name p because I'm not going to use that p anywhere else. So let me go ahead and erase that so I don't confuse myself later. And I'll just make a note that this was the perimeter. Okay, now I have this equation, and I'm going to use this new information to replace one of these variables in my the quantity I want to optimize. So let's go ahead and in this case, you can solve for either x or y. Sometimes it's easier to solve for one variable versus the other, but in this case, they're the same difficulty. So let's just pick one. Let's solve for y. Okay, so if we solve for y, I would subtract 2x from both sides. And then I would divide by 2 here to get y by itself. Okay. Now that I have y on its own, and it's in terms of x, I can go back up here to my area equation, and I can replace this y with the expression involving x. I know that y is equal to 50 minus x. So instead of y here, I'm going to write 50 minus x. Okay. So now, I guess I could scroll down a little bit. Now we had area is x times y, but instead of y, I'm going to say that's x times this quantity that I just found, 50 minus x, because I just found that if my rectangle has perimeter 100, then y is equal to 50 minus x. So I'm replacing y with that expression. This tells me that the area is equal to 50x minus x squared. This is now an equation in one variable. It's just with x's, there's no more y's. So we can go ahead and find its critical points. This is what we want to maximize. We want to maximize the area. Okay. Now, with the extreme value theorem, so go back up here, we're supposed to check the critical points and the endpoints, but we weren't explicitly given any endpoints in this problem. We actually need to figure out what makes sense for the endpoints. So we need to know what's the domain of A. In other words, i.e., what are the endpoints of x? Like, what am I allowed to plug in? Okay, remember that x and y represent the sides of a rectangle. So it would make sense that this rectangle's sides are not negative, because it doesn't really make sense to have a negative length. So I'm going to say that our variables x and y both need to be bigger than or equal to 0. I'm going to allow them to be 0, even though it seems silly to have a rectangle with a side length of 0. That would be like just a line, like we're like collapsing our rectangle onto a line. But I'm going to say that, I'm going to allow for that to happen. So bigger than or equal to 0. Okay. Now, just as a reminder, though, y we found in terms of x, we said that y was equal to 50 minus x. So let me go ahead and replace y by 50 minus x. And that tells me that 50 is bigger than or equal to x. These two pieces of information now tell me that x is between 0 and 50. And now I have my endpoints, 0 and 50. Okay, so we are going to, using the extreme value theorem, the maximum will occur at either an endpoint or a critical point That's true for continuous functions, and our expression, our equation for the area is a continuous function. It's a polynomial, so we're free to use that. Okay, so we have our endpoints, 0 to 50. Now we need our critical points. What are our critical points? These are points where, in this case, we're calling it A. So A prime of x is 0 or does not exist, or it's undefined. Well, A of x was, let's remind ourselves, 50x minus x squared. So A prime of x is 50 minus 2x. We're just doing a quick power rule there. If I set this equal to 0, that tells me that my critical points occur when 50 equals 2x. In other words, when x equals 25. The derivative here is also a polynomial, so it's defined everywhere, so I don't really need to worry about the does not exist case here. All right, so now I have these contenders for points that might be the maximum, give me the maximum area. So we need to check critical points and endpoints. When I say check, I mean that I'm going to evaluate A, the area, when x is 0, when x is 25, and when x is 50. So if I evaluate A of x, and just as a reminder, A of x was 50x minus x squared. So if I plug in 0, I will get 0. If I plug in 25 for x, you can check this in a calculator, or you can go off to the side and do some scratch work, you'll get 625. And if I plug in 50, I'll have 50 times 50 minus 50 squared. 50 times 50 is the same thing as 50 squared, so I'm going to get 0 here too. So my maximum area, this gives me the max area, okay, when x is 50. When x equals 25. Ooh. Okay, when x equals 25, I get the max area. When x equals 50, I get 0. Now, this is not the answer to the question. The question asked, let's remind ourselves, it's always good to reread the question. We're going to go all the way back up. Find the dimensions of the rectangle. Go ahead. We want the dimensions of the rectangle. That means I want to know what's x and what's y. Okay, we have x. So the dimensions of the rectangle are x equals 25 meters. And I know the units from the original statement of the problem. We were told the perimeter was 100 meters. So I know that my sides are in units of meters. So when x is 25, and y we found was 50 minus x. But I know that x is 25, so this is 50 minus 25. So y is 25 meters. This is the answer to the problem. I was asked for the dimensions, and so my answer should give the dimensions. Okay, that's it for this example. Let me know if you have any questions.